So hi everyone, and welcome to this new seminar of our Clever Planet Fall 2022 seminar series. My name is Maxime Maurice. I'm a postdoc at Rice University, and I'm your host for today. So before I introduce you our speaker for today, I'll proceed to our little ritual as usual, and I'll start saying a few words about the Clever Planet project, which is a multi-institutional interdisciplinary initiative to unravel the conditions of planetary habitability in our solar system and beyond. Its lead institution is Rice University, and it is supported by NASA as one of the team in the Nexus for Exoplanetary System Science, Nexus Coordination Network under astrobiology. And we also like to proceed to a short land acknowledgement because our research at Rice University is pursued on the traditional lands of several native peoples, namely the Karankawas and Sanas, as well as the Corawiltekans, represented today by the Tapilam Corawiltecan Nation, and the Aishaks, represented today by the Atakapa Ishak Nation. And we see it as our duty to acknowledge this historical aspect of our identity and to foster beneficial environments for all communities, in particular those who preceded us on this land. All right, and this is now my great pleasure to introduce you our speaker for today, Yoshinori Miyazaki. Dr. Miyazaki is a Sandbach postdoctoral fellow at Caltech in the Center for Comparative Planetary Evolution. He did his undergrad at University of Tokyo and his PhD at Yale University, working with Jun Korenaga. And he has been working on a fairly broad spectrum of topics, going from magma ocean crystallization to protoplanetary disk processes. And today he'll be talking about volatile degassing from the planetary interior and its implication for habitability. Brief reminder, as usual, if you have questions, you can either keep them for the end of the talk, or if you're afraid you're going to forget them, you can also type them in the Q&A and they will be read at the end during the question and answer session. And yes, without further ado, Yoshi, take it away.
Hi, thanks, Maxime, for the introduction. Please. All right, screen looking good?
Yep.
All right, thank you. Thanks, Max, for the introduction. And thank you so much for having virtually having me today. My talk today tries to answer the question of how the mass and composition of the atmosphere was determined on terrestrial planets. Now, I'll be mainly focusing on mantle degassing side in the period from the magma ocean to the mantle convection stage. And the reason I'm interested in this problem is because obviously the atmosphere plays a critical role in determining the habitability. And to assess the habitability of exoplanets, we need to understand how the atmosphere is formed in the first place. Just as a general background, but I would like to start off my talk with asking what habitable actually means. Now is a really exciting period for planetary scientists because we're now really discovering new exoplanets more than one per day. And this is pretty amazing considering that when we, I don't know you, but I was born, we didn't even know a single exoplanet. And now we have 5,000 of them. And depending on who you ask, but there are pretty much more than 20 potential habitable Earth-like planets in the entire universe. And I expect we're going to find more of these very soon. But what I want to ask here is how can we decide whether these planets could be habitable or not? The criteria to be on the list is based on they're using Earth similarity index, but the background of the concept is the habitable zone. I think it's you may have heard of this concept, and it's pretty straightforward. It shows a distance from the host star that liquid water could be stable on a planetary surface. The habitable zone varies with stellar radiation, radiation, and planets listed on the previous slide lie in what's called in this kind of habitable zone over here. But habitable planet doesn't necessarily mean that it is like ours. And creating an Earth-like planet is much more complex than simply putting a planet around the right distance from the central star. And we can just look at the neighboring planet, Venus, to see how important of a role the atmosphere could play on the surface. Venus is inhabitable simply because it's outside the habitable zone for now. But on top of that, it has a crazy atmosphere with 90 bars of CO2. It produces an extreme greenhouse effect, and its surface temperature reaches as high as like 480 degrees C. If the Earth had a 90 bar of CO2 atmosphere, the surface temperature could also be very extreme. This figure shows how surface temperature changes with CO2 pressure and solar radiation. X-axis shows the absorbed amount of radiation, and each line over here represents different levels of atmospheric CO2. Earth currently locates at, I want to show a pointer. I'm not sure how to do that. Anyway, I'm not sure whether you're seeing my cursor or something, but Earth currently lies on this bottom over here. Like was in the bottom one is around like 240-ish, like it was net solar radiation with like surface temperature around 300 K. But if Earth also had a 90 bar of CO2 atmosphere, the surface temperature is going to increase to nearly 250 degrees C. And the atmosphere could be in a supercritical state near the surface. If you see the right shows the carbon dioxide phase diagram. So liquid water could still be stable at the surface, even if the Earth had a 90 bar of atmosphere. And by the definition of habitable zone, Earth is habitable in that condition. But the surface condition would still be very different from what we think is a habitable or what we, like a human being, can survive. We do not have a supercritical fluid on the surface like the current Venus. And it's important that Earth has the right amount of CO2 in the atmosphere. I will note that Venus cannot stabilize liquid water regardless of CO2 amount. And that is what happens when a planet is outside a habitable zone. And there's another discussion about that. So I will just leave it there for now. So why does two planets have such a different amount of CO2? Plate tectonics and carbon cycle are no doubt a huge factor. And many people are working on this issue. But I would like to answer this question by investigating how volatiles are getting partitioned between the surface and the interior in a general sense. A large amount of volatiles could actually be stored in the crust, mantle, or core, and volatiles are in general not favored in the mineral phase, but the mass of the mantle is so large that it could hide a significant amount. CO2 gas in the atmosphere is probably, we would have more than orders of 5 to 6 orders of magnitude larger amount of CO2 hidden in the crust and the mantle, and we may have more in the core. The amount hidden in the crust and the mantle is so large, so what we want to focus here is the partition between the mantle and atmosphere. And here I will be focusing on how mantle degassing would characterize the volatile budget, and a disclaimer that as I described in this figure, core could also be a large reservoir. But I'll be starting off my discussion from a period after the core was shielded by a solidified layer, and volatile exchange between the core and the mantle already became inefficient. So, and the goal to the talk will be to mainly focus on how mantle degasses and then investigate the history of mantle degassing. So that's for the kind of general background. And I would like to go all the way back to the point when that planet was formed, to the giant impact. Planet formation theory tells us that the terrestrial planets experience several giant impacts at the final stage of formation. Models shows that this energetic impact melted most of the mantle and produced an ocean of magma all the way down to the core mantle boundary. This resets the volatile partitioning between the surface and the mantle and sets the initial condition of the surface volatile budget. After the giant impact, the temperature of magma could reach as high as 4,000 degrees C, and that means convection was likely to be extremely fast. The overtime time scale, so that means from magma to travel from the surface to the bottom and back to the surface again, is on the order of weeks. This is much shorter than the lifetime of a magma ocean. So volatiles, it pretty much became between the magma ocean and the atmosphere, was likely to be in an equilibrium state. So we can predict the amount of volatiles in the magma ocean and atmosphere using the solubility to silicate magma. The right plot shows one of the compilation of experimental data. And it's a little hard to see, but blue line shows the water, red is the carbon dioxide. And I'm highlighting those two, and especially in the region of like 10 to 1,000 bar, which is relevant over here. In this region, water is much more soluble to silicate magma compared to carbon dioxide. And we use this solubility measurement to predict the fraction of volatiles that are kept in the magma ocean. Based on the data, we did a very simple calculation of volatile partitioning. Because the solubility increases as partitioning at the surface determines the volatile budget. When a total of 1 ocean mass of water is present in the magma ocean and the hydrosphere, so basically above the core, the majority of water would reside in the mantle, and the amount of water at the surface would only be around like 7 bar. You can see that there's more than 3 orders of magnitude difference in the amount residing in the atmosphere, in the mantle. But on the other hand, more than 70% of the total carbon dioxide will be released to the atmosphere. So the atmosphere on top of the magma ocean is likely to be extremely carbon dioxide rich. So here's what's going to happen afterwards, though. The degassing doesn't stop over there because magma ocean solidifies, and when that happens, volatiles are incompatible elements, so they tend to concentrate in the melt phase. But it's not actually that obvious that all volatile would degas when magma ocean completely solidifies. To understand how much of it actually solidifies, I would like to briefly go through how this sequence of magma ocean solidification goes like. And actually, the word magma ocean is actually a bit confusing because when people say magma ocean, it implies that it's like an ocean of liquid magma, but we still call it magma ocean even if after it cools down and crystals starts to interconnect. In those layers, the magma layer would turn into more like a mushy state. And this transition happens from the bottom as melt fraction reaches 40%. And when that magma goes through a kind of transition, viscosity would increase by like orders of magnitude, like probably 10 or all the way up to like 20 orders of magnitude. If that's the case, we call it a magma ocean, but the rheology will be similar to the current mantle, but yet trapping a significant amount of partial melt. This partial melt could include a concentrated level of volatiles, but because they exist in isolated pore space in the solid matrix, the volatiles may never be released to the atmosphere. This solid layer would efficiently be cooled by Rayleigh-Taylor instability, and the partial melt would solidify within the solid layer, ending up being trapped inside a deep mantle. So even as magma ocean solidifies, the volatile concentrations in the near surface magma layer may not actually change that much. That process that could release the volatiles out of this kind of solid mushy state is melt percolation. Imagine squeezing water out of a cleaning sponge, but instead of your hand pushing the water out, the density difference between the solid and liquid will be driving the flow. The efficiency of percolation is actually highly uncertain because it depends on the grain size of solid matrix, and that is something we don't have a great understanding on. But on top of that, there's a gravitational instability going on inside the magma ocean. And when the instability happens, it would transport the solidified layer fast downwards, faster than the melt can actually escape the percolation. And when those kind of mixing happens, it experiences adiabatic compression, and the partial melt would solidify within the deep mantle without degassing the volatiles. So a large number of volatiles inside this solid layer could be sequestered in a deep mantle. There's examples of volatile degassing during magma ocean solidification. I just talk about the qualitative number, and but in general, it's Rayleigh-Taylor instability tends to be very fast. We can easily estimate that it could be an order of like weeks, and I mean even in the longer times like years to 10 years, which is still very short compared to magma ocean timescale. And if you think of, then here, we need to assume some sort of volatile percolation as efficiency to estimate that volatile release. And I took like two of the models from, one from the Hirschman's group, and one of the right is the model I made. There's a difference in the efficiency of compaction over here. And those that would have created uncertainty in the results. But I think two things are robust over here in both figures. One is that most of the carbon dioxide would reside in like more than 90% of total budget would be released to the atmosphere. If you see both graphs, it's green in the left one and blue in the right one. And the second thing is that a certain amount of water would be kept in the mantle, whether it's like it's more than 90%, or this figure shows more like a 70-ish% on the left. That is uncertain, but I would emphasize that mantle should have been somehow pretty much wet after the solidification of magma ocean. And so the volatile amount in the surface could be very limited. And also mantle could be wet, which is very important for the rheology of the subsequent evolution. So what does this calculation tell us about the presence of liquid water at the surface? Here I will be taking a conservative estimate, so a kind of lower bound estimate for the liquid water amount at the surface. But for water to be stable as liquid at the surface, a basic criterion is pretty simple. The amount of surface water needs to be larger than the amount that atmosphere can contain as water vapor. In an extreme greenhouse effect with like more than 100 small bars of CO2, the atmosphere can contain a lot of vapor compared to like the present day atmosphere. For example, with a volatile concentration I used in a previous slide and I plotted over there like 300 ppm, around like 5 times 10 to the 19 kilograms of water vapor would be present at the surface. But with 300 ppm of CO2, the atmosphere that could be water vapor that could be stored in the atmosphere could be as high as like 4 to the 10 to the 19. So it's just only slightly above the total amount of water vapor that can be stored in the atmosphere. So the liquid water that's among all the surface water, only like 20% of them would actually exist as liquid water. So we can still argue that liquid waters are stable on a Hadean Earth-like environment, but it will be very different from a present day Earth with like a very thick ocean. And that's the case for Earth. But if we move on to Venus, it's not trivial that Venus can even stabilize the liquid water. This figure in the right shows how much surface water is needed to stabilize as a liquid. It's not obviously, actually, to be honest, very easy figure to read, but x-axis shows the flux we're receiving. So left here, I plotted where the Earth would be like, and the right is for Venus. And if you have more CO2, that's within the y-axis, we need more water to stabilize liquid water. If we move from so if I assume water and Earth and Venus also both had the same amount of CO2, but moving from this Earth point to the Venus point, the amount of water vapor that could be contained in the atmosphere could increase by a factor of 2 or more, depending on how much Venus received their flux. So water oceans, and if in that case, if the amount could increase to more than 8 to the 10 to the 19 kilograms of vapor in the atmosphere, so that could be larger than the amount of surface water degassed during the magma ocean period after it's solidified. So even if Earth and Venus had the same volatile budget, it could mean that no water oceans could form at the surface of Venus. So that's kind of a general sense about what happens during the magma ocean stage. And there, kind of simplified argument, and there are a few things that I didn't consider in my discussion. So I won't go into details, but I still like to acknowledge those. The first is about the issue of redox. Volatiles coming out of magma ocean could be more reduced rather than water or CO2. It could be like CO and H2. And there's several papers coming out of this. I hear like it's almost people at Rice are also working on this. It's another complicated issue. I would just leave it there that's possible. My assumption over here is that it's made of H2O and CO2. The other is the effect of tidal heating. I said like percolation would be it could be kind of hindered by the Rayleigh-Taylor instability. It would be sequestered in the mantle. But if tidal heating kind of like maintains a partially molten period for long enough, it could lead to significant degassing. These are important, but like I think this could be another topic for an hour of talk. So please allow me to leave it with simply acknowledging it. So that's the magma ocean stage. So now that we find out the initial condition, I would like to start talking about the atmosphere, what happens after it solidifies. So the key here is now moving on to solid convection, and it's more about the mode of mantle convection. And a mode could be largely separated into two modes. One is stagnant-lid convection, and the other is plate tectonics. Needless to say, Earth does have a plate tectonics, but all other planets that we know of are at least operating under stagnant-lid convection. And this is more of a natural kind of convection because, to put it in a very simple term, cold rocks are really viscous. So it takes a huge energy to break them down and stuck them inside the planets. How plate tectonics can be initiated is just another huge topic, so I won't go into there. But what I want to instead talk over here is how volatile exchange could be different between these two modes of mantle convection. The biggest difference is whether the surface becomes recycling or not. When a new surface is created and old one is subducted back into the mantle, we can transport volatiles from the surface back into the interior. Volatiles ingassing, so that means volatiles ingassing could be very limited for stagnant-lid convection. There could still be some weathering happening. There's a paper on that, by how carbon cycle affects stagnant convection. Its amount degree will be still very limited compared to plate tectonics. So I will neglect that factor for now. The same actually goes for outgassing. This cartoon shows how mantle degasses could be different between these two modes. So this, to talk about, this may be a simple thing, but like to talk about how degassing occurs. So mantle goes through upwelling during the convection, and it starts to melt when it hits the solidus. When it hits the solidus, mantle melts, and volatile concentrates the melt phase, and the melt escapes to the surface. Volatile gets degassed together with them. So for plate tectonics, this process is very efficient because the upwelling mantle could reach all the way up to the surface, just beneath into all the way to the surface, and create crust and depleted mantle. But for a stagnant-lid convection, the thick lid could limit the degree of upwelling, and a smaller amount of melt will be generated compared to plate tectonics. So I calculated the rate of degassing for a plate planet under a stagnant-lid mode convection, stagnant-lid convection mode. 3 lines here show the amount of degassed water at the surface. I'm using a heat flow scaling established by Solomatov and Kornaga. And the initial amount is determined by the model I showed before. It shows that kind of the lower bound estimate that percolation is very inefficient. And this gradually increases, but let's take the line with this yellow one, like 1.2 ocean mass of the total water inventory, which is like the lower estimate for the current Earth. So at the beginning, there should be around 10 to 20 kilograms of water at the surface at least, but the rate of water degassing afterwards is pretty slow. It's only around like 10 to 20 kilograms per billion years. So even after 5 billion years of evolution, more than half of the total water inventory could remain inside the mantle. That goes for all 3 lines that I assumed over here. The situation is actually even worse for like super Earth. I won't be talking a lot about exoplanets. This is the only side I would use the word super Earth, but it's actually pretty worse, because if you look at this figure over here, you can see that degassing stops after like 2 to 3 billion years. This is because, when a planet starts to cool down, the depth where melting starts going to be shallower and shallower. And for super Earth they have a stronger gravity, and pressure is higher even at the same depth. So say Earth and Earth-sized planet and super Earth have same thermal state and the same mantle temperature, and the mantle would both start to melt at 2 GPa. For an Earth-sized planet, the melting depth may be below the stagnant lid, but for larger planets, it could be buried inside a stagnant lid. So even if the mantle upwells, it never actually reaches a depth where it starts to melt. So the mantle won't actually degas at all at a certain depth. And that also happens for an Earth-sized planet, but it takes a much longer cooling timescale to actually reach that stage. So this is a kind of summary of results for that I calculated for the degassing rate for different rates, different volatile concentrations. And because under stagnant convection, degassing could be very slow, or even stop after some time. So if you look at this figure, it shows when the water ocean could form under each kind of conditions. 2 panels here on the top shows the case for the Earth, and the bottom are the case for super Earth is. Y-axis is the water amount, and x-axis is the CO2. So the corner in the top left corner is more water, less CO2, and as you can guess, water oceans would exist from the beginning. But if you go to the other side of the corner, on the right bottom, that means less water, more CO2, we may actually never see oceans form on the planet. Gray-sided areas on the right bottom corner corresponds to such a condition. This trend is the same for any size of planets over here. Left and right shows the indicate the location of the star, and the left receives an early Venus-like radiation, whereas in the right is like early Earth-like. For Earth-like radiation, if we wait for long enough, water oceans are most likely to form on a very wide parameter range. This black rectangle in the middle shows the amount, estimated volatile amount for silicate Earth. So if you look at the top right figure, like one Earth-sized planet of like early Earth-like radiation, pretty much Earth is water oceans are expected to form. But if planets start to receive a Venus-like radiation, hydrogen escapes start to be significant as well. So as the water degasses, it could readily escape, and water oceans may not form even if the Venus had a volatile content similar to bauxite Earth. So what this result shows is that a large planet under stagnant-lid convection could naturally evolve to have a Venus-like condition. At first, the atmosphere is rich in CO2 and most water is retained in the mantle. Under stagnant-lid convection, CO2 remains in the atmosphere. There could be some weathering, but like we're talking about like hundreds of bars of CO2. So that would probably, that kind of degree amount would remain in the atmosphere. And water degassing is too slow to beat a hydrogen escape, and it may never form water oceans. Even in the region that liquid water could form, the water amount is going to be very limited, and we have massive CO2 atmosphere. So the condition would be very different from an Earth-like environment. So stagnant-lid convection is unlikely to create a surface environment similar to Earth. So now I would like to ask like whether plate tectonics can create an Earth-like atmosphere. Instead of starting with this theoretical argument, I would like to go into some facts about the early Earth. This is a history of CO2, like estimated from carbon cycle, with some like actual estimates from the geological evidence. And it shows that CO2 pressure at the end of Hadean was on the order of like 0.1 to 1 bar. This is still higher than now, but it's not at the level that is created after magma ocean solidification, which is like hundreds or 300 bars, and some estimates goes up to like thousands. And if you look at Hadean zircons, we also find an evidence of the surface environment being very similar to present-day conditions even 4 billion years ago. Zircon is an extreme durable mineral, so they can tell us information about time when we have no record samples from. A titanium thermometer shows that crystallization temperature of zircon is around 700 degrees C, and to explain such a low solidus temperature, near water saturation is needed. And also we also find some like mineral inclusions like muscovite, apatite, and biotite, which are all hydrous minerals, and they also indicate the presence of surface water in the host magma as well. And I won't, there's a lot more to talk about with zircons, but there's a lot of evidence that lines of evidence suggest that liquid water was present. And also the redox condition and the mode of subduction was also likely to be pretty similar to the present day condition. So it seems that Earth managed to remove a huge amount of CO2 in a pretty much short time. And this issue was originally realized by Zhang Li asleep, and they published a few papers out of this idea. And they predicted that this is possible because plate tectonics was really active in the Hadean. They mentioned that lower viscosity let foundering of crustal blocks sink more quickly. And it's true that if the seafloor was renewed pretty often and weathering was efficient, carbon could have been efficiently sequestered back to the mantle. And active tectonics in the early Earth looks like a reasonable concept because we can also point to some geochemical data to support it. For example, like 142 neodymium isotope data has been suggested to indicate an efficient crustal recycling due to the Hadean period. But this is actually a huge but general argument that hotter planet convect comes from like hotter mantle has a like lower viscosity. But if we look at the more of like geodynamical perspective of the geological data, it actually suggests that Earth didn't really convect faster in the ancient period. The left plot is a thermal history of the Earth, and it shows that it goes from so like oh my god, I made a huge mistake, but like it left the top and bottom actually has a different direction. fraction of the time. So the top figure shows that from left is old and right is new. So you can see that the temperature roughly stays constant and it starts to cool down after like in the last 2 billion years. And I'm sorry for this confusion, but then the bottom figure over here, the time goes from right to left. And if you see that this over here, plate velocity actually stays pretty slow in the first few billion years and actually starts to speed up in the last billion years, even though mantle started to cool down. And this kind of could also be seen in the kind of trend is also be seen in supercontinental cycle. Right figure shows the number of zircon sampled, and the key can be roughly, if not directly correlated, but like roughly correlated with the formation of supercontinents. The longer supercontinental cycle means that it needs to be needed more time to bring together continents again. And this also suggests like the plate motion was actually slower in the past. And this could be counterintuitive because, as I said, hotter mantle, lower viscosity is a kind of a general concept. The reason is because of the melting below mid-ocean ridges. The partial melting of the mantle becomes the source for what's left the crust, but it also leaves a depleted lithosphere, which is dry because of melt extraction. Dry olivine has a higher viscosity by a factor of 100 or maybe 1,000. So under a hotter mantle, more melt will be generated, so the oceanic crust and depleted lithosphere becomes thicker. Subduction becomes harder, and because dry depleted lithosphere has a higher viscosity than the ambient mantle, and if you take into this account of like dry and stiff depleted lithosphere layer, we can actually naturally explain the slower plate tectonics in the past. We quantified the thickness of crust, depleted lithosphere, and plate velocity under feet flaw scaling. The left shows the estimated thickness of basaltic crust and depleted lithosphere. With a mantle hotter by like 300 Kelvin, the depleted lithosphere grows to like nearly 3 times the present day value. This layer is drier and stiffer, so plate velocity becomes harder to subduct when such a layer is so thick. Also, plates become more buoyant, take more time for plate to cool down and become heavier than the ambient mantle. So with these effects combined, plate motion in the Hadean is actually predicted to be similar to the present day, even if the mantle was much hotter. I'm showing the button over here, but now I'm using scaling this. I'm using a scaling law to fit with a current velocity of 5 centimeters at 1350 degrees C. And if you use a value of 1600, roughly estimated for the Hadean mantle, it only increases slightly to like 7 centimeters per year. So if plate velocity was the same as now, how long would it take to remove, say, like 200 bars of CO2? I'll make a very rough argument about the geochemical side over here. Let's assume all magnesium and calcium silicates were used to form carbonates. And in that case, the seafloor could hold up to like 10 bars of CO2 at one time. The seafloor then has to be renewed like 20 times to remove 200 bars of CO2. And if you use the present day renewal cycle of the oceanic crust of like 90 million years, it takes around 1.8 billion years to remove all CO2 from the atmosphere. And I would say this is a very optimistic calculation because the actual number should be much larger. We are assuming that carbonates don't melt or decompose during subduction, and the amount of CO2 stored at the seafloor could be smaller than 10 bars in reality. The present day value is around like 2.5, and 10 bars is actually a pretty generous estimate. So if that's the case, was the surface in an extreme greenhouse state until late Archean or even to like early Proterozoic? And that seems against the general geological evidence, and because like I don't think we can explain like 200 of bar of CO2 for 2 billion years. There is one assumption that we are making so far that could be changed, and that is that Hadean mantle had these. What we're assuming over here is that we are assuming a same pyrolytic composition for the Hadean mantle as the present day. But magma ocean was just solidified, and differentiation during that stage could be significant. So the mantle structure may have been very different from the present day mantle. This image shows how magma ocean differentiates and how it evolves during the solidification process. I took it from Maxime's paper that he published a few years ago, and color shows the compositional field. And it gradually fractionates, but they also get mixed. So as the magma ocean evolves, the mantle starts to get separated into compositionally distinct reservoirs. In this figure over here is from like greenish, yellowish one, and that's kind of formed earlier, that's solidified earlier, versus to a reddish one that's kind of remaining into the last period. I solved for such composition of fractionation using a thermodynamic model. And the results shows that the oily forming materials, it forms solids from bottom to the top. I'm not calculating how it mixes afterwards. So it's a much more simpler model than what Maxime does, but focusing on the thermodynamics over here. So the bottom part is more of a color correspond to like green to yellowish that's forming from the bottom, and that would eventually go to the upper part of the mantle. And at the last remaining part will be extremely enriched in iron, so that they will become gravitationally stable and probably exist as small blobs or sink to the bottom of the mantle. So what this shows is that, what this shows is that after the solid magma motion differentiation, the majority of the mantle would be made of like a very high Mg content, like as high as 95, and iron depleted. And this is much higher than the pyrrolite mantle, which has like a value of 89. And that has a huge consequence for the melting behavior. I will simplify the situation a little bit and assume that the mantle is made of two compositions of distinct reservoir, the high Mg number matrix and iron-rich reservoir. The near surface region, like that shows in greenish, yellowish, is mostly composed of the left one, the iron-depleted materials. Minerals with low melting temperatures, like feldspar, CPX, they are mostly concentrated in the iron-rich side. So the remaining high Mg number matrix would tend to have a much higher solidus than the original pyrolytic mantle. Here I use calculated phase diagram over here of two components using the MELS program. Contours shows the melt fraction, and this is blue is the solidus and the red is the liquidus. And so the green line represents the adiabat of like 1600 degrees C, estimated for Hadean mantle. Pyrrolite starts to melt at like 5 GPa under 600 degrees C, but this high Mg number matrix won't melt until 2.5 GPa. Iron-rich reservoirs will melt at the deep down around like 8 to 10 GPa, but it is in the deep mantle or it exists as small blobs. So that kind of melting won't create some sort of like uniform like melting behavior of the near surface region. So this is the picture I proposed for the surface structure of the differentiated mantle. High Mg number matrix melts at 2.5 GPa and form a high Mg number crust. And iron-rich reservoirs would exist in deep mantle, and some of them may exist like small blobs. So, but even if they melt at a deep depth, it only melts like locally, and would not be dehydrating the entire near surface mantle. So compared to like a pyrolytic mantle I show on the left, the differentiated mantle would have a thinner crust and also a thinner dry depleted lithosphere layer. And so this thin dry depleted lithosphere means thinner stiff layer. So that means plate velocity could be much faster than the case of a pyrolytic mantle. So again, I used the crust thickness of crust depleted lithosphere, and I estimated that for the MELS program. And I used that thickness to calculate for the plate velocity, which is based on the scaling law. Now, if you look at the figure on the left, the depleted lithosphere thickness decreases by a factor of 4. So unlike the pyrolytic mantle, the plate velocity is not limited by this like stiff layer at the top. At 600 degrees C, plate velocity could be as fast as 50 centimeters per year, which is like roughly 10 times faster than the pyrolytic mantle. I would like to note that this calculation is assuming that mantle is wet, and this is where a slow compaction of magma motion actually matters. If the mantle was completely dried out, this viscosity on the mantle would increase by like a factor of 100 or thousands. And for reference, when the mantle is hotter by like 250 degrees C, that temperature effect would decrease the viscosity of roughly a factor of like 20-ish. But so this is still very small compared to the effect of water which could change the viscosity about like 100 or 1,000. And if the mantle was completely dry, even if the mantle was hot, that means the plate velocity would decrease to roughly like 2 centimeters per year. And it will be even slower than the present day mantle for a Hadean one. And so this is kind of an indirect constraint, but this also kind of suggests that the mantle should not have been completely dehydrated after magma motion solidification. So now we know the plate velocity, we could estimate the speed of carbon sequestration, and it's very different between a paralytic mantle and a differentiated one. If the mantle was differentiated and became heterogeneous, a stiff lithosphere would be thin, so the surface could be renewed every 10 million years. And on top of that, higher mantle temperature results in like a more OPX and olivine content in ocean and crust. So it has a more capacity to store and form carbonates. As these two effects combined, the surface temperature can drop to the modern level in around like 150 million years, which is much shorter than like the billion-year timescale showed earlier. The left figure shows the evolution of the atmospheric pressure, and the right is the surface temperature. In this case, I think we can say that the habitable environment has very likely emerged by the end of the Hadean. But on the other hand, for a paralytic mantle, this is an estimate that I already made a rough estimate up here, but this is just to show with the figure. But if it only renews every 90 million years, it takes like nearly 2 billion years to draw down 200 bars CO2. And again, we're assuming that all carbonates that being delivered to the mantle, so this timescale could actually be much longer. So the planet is likely to have started off a journey with like a thick CO2 atmosphere. The atmospheric evolution after that would differ with whether plate tectonics operates or not. With stagnant-lid convection, water could be largely retained inside the mantle, and maintaining CO2 atmosphere the CO2 atmosphere will be maintained because there's no significant ingassing process. That being said, even with plate tectonics, it could take a long time to stabilize liquid water ocean and remove a huge amount of CO2. Plate velocity could be limited and it could take billions of years to form water oceans, but at least for the case of Earth, it seems like it happened earlier. And the key to removing a massive CO2 in such a short amount of time may lie in the magma ocean period, so that they actually differentiate it and it will allow for a very fast plate motion. So there might be a link between how magma motion differentiates and creating a clement surface environment on the terrestrial planets. Actually, I will skip that for now, and it's kind of 45 minutes. So, to summarize, like what I over here is to track the degassing history of terrestrial planets. This is kind of like a popular topic recently. There are a few other papers here, but over here, I mostly focused on the geodynamic side of the evolution. And what this says is that atmosphere started off with a CO2 atmosphere, but it's most water is likely to actually be retained for many cases. Yeah, so that's kind of my take-home message, and please let me know if you have any questions.
Great, thank you very much. Great talk. So yeah, if you have questions, please raise your virtual hands and you will be designated to speak, or you can also write your questions in the Q&A. And I see that we already have a question in the Q&A section by Maitreyi Bose, who says, great talk, Yoshinori. Thanks. The question is, what were your assumptions about hydrogen or H2? What will happen if you included it in your simulations? Is hydrogen being ingassed while CO2 being degassed?
It's great. So when you mention H or H2, so there's I'm not sure whether you refer to like hydrogen, like a reduced one, or the more of like water one. But I will start mentioning about the water. So in this model, it's just water is kept degassing, and it's not being considered to be ingassed back to the surface for like these kind of so in these kind of calculations. Oh yeah, okay, reduce one. But just to finish off, I'm not thinking about how water is being transported back. I don't think we have a great understanding of the rate how it happens over there. The second thing, when it comes to H2, the assumption over here is that we are assuming like some sort of like serpentinization reaction taking place. So water and olivine gets reacted, and H2 is being formed. I am thinking about the hydrogen escape over here, but for Earth-like scenario, it's not significant, and it won't. So it's actually possible that it could actually have a buildup in H2. Thinking about this side, I'm just assuming like the fusion limit, they escape at the top, and so that's kind of the basic assumption. Does that? I hope that answers your question.
I can allow you to talk, Maya, actually, if you want to.
Thanks. Yeah, I have a sore throat, so I don't know whether I'll be able to talk too much. But yes, I was curious about H2. And so you assume in your models that you're losing it from the system completely. But
Yeah.
but what if you don't lose it? I mean, can you, based on your simulations, can you speak to that a little, or?
So when you say like loss of hydrogen, so like are you mentioning to like the escape to the space, or like those kind of things?
I mean, that's what you, so do you include hydrogen in your simulations at all, or not? Or is there a H2 over CO ratio you assume, or is that not even a part of your?
So yeah, so I'm assuming that a atmosphere, so there's a huge argument about like what's the atmosphere like after the magma ocean solidification, and there's a few people say it could be very reduced in H2 and CO, but the basic assumption over here is that H2 and CO2 is like pretty, mantle was oxidized enough so that the volatile was in H2O or CO2 form. And that's being said, it could still form H2 afterwards through like serpentinization, and that is included. But I think, I don't think for larger planets, I mean, there's some debates, but if you go to like Earth, like planets larger than Earth size, volatile was, at least for the major part, out of degassing side, will be mostly in H2 or CO2.
Okay, I'm thinking from the point of view of these papers that I've read about hydrogen being ingassed in the magma melt state, and then you have the melt go into the mantle, enriching the mantle with hydrogen.
Yeah, so that's possible when you think about like in large exoplanets, I think sub Neptunes or something like that. If it contains like if it acquire hydrogen from like nebular gas, that's also possible. But here the most of the focus is on like the oxidized like, terrestrial planet-like stage, and that's kind of assuming that it's redox, it's in the oxidized state. There's another very huge argument, like what happens. It's actually very different because the solubility changes and everything changes. So I at least I don't think there's much to take off from my talk from that perspective. I think we need to change a lot of assumptions that I showed over here.
Okay, thank you.
Right, we have a question from Devjit Patak, who says, how does carbon cycling efficiency in the subduction zone affect the timescale of CO2 drawdown?
I mean, simply if it's one factor is that if it mostly, and there's actually two factors. So when it decomposes, carbonate decomposes, it melts, or it could either be transported to the melt phase. Whether that actually gets released to the atmosphere or not is another huge factor. If like the present day carbon cycle model, some people say that carbonate dissolution happens in subduction zone, but everything is actually kept in the crust, but doesn't actually be released to the atmosphere. So if that's the case, it may not actually matter for the timescale of CO2 drawdown. But if it does, even if you kind of form it and try to subduct it, CO2 could keep kind of coming back to the surface, and the degassing, the drawdown timescale could be like infinitely long. Yep.
Right. Do we have another question? So I had a quick one, which is just maybe speculation, which is so your model, if Venus was formed with the same water budget than Earth was, your model would suggest that Venus' interior is rich in water, right?
Yes, that's some kind of something what this model says. And obviously, there's been a much more elegant model by Christus and Totten that modeling like a Venus-like atmosphere. So in those cases, we would have like a huge amount, like we would have to escape, like readily escape the hydrogen as it degasses. So if people want to use this kind of, if I say I was correct, that means there should be like a huge amount of oxygen that's being kind of like used to oxidize these Venus terrestrial material so that we don't see any oxygen in the Venus atmosphere.
Okay, Raj, go on, please.
Hi, Yoshi. Great talk. Quick question. Maybe I misunderstood. You had one slide where you compared stagnant lid case for Venus as well as like a stagnant lid type of case for a super Earth, and my recollection from that slide is you implied that perhaps for super Earth the lid thickness is so big that you would completely suppress melting, right? And there may be a small amount of melting for Earth-sized planet. Now, this my understanding from this slide is this is relevant when you already formed the lid and so on, like kind of in a mature mantle convection state. But what's the process leading to the formation of this thick lithosphere? I mean, are you considering the definition of the lithosphere from entirely thermal point of view or chemical point of view? If the latter, there would be some initial degassing leading up to the formation of the lid, right?
So actually, there's an issue about that's relevant to that, what you just mentioned. But what I'm trying to say over here is actually a little more simple. Assuming that the lid thickness is similar, the base of the pressure will be much higher for super Earth because of the gravity. So even if it has like the same like lid thickness, it's much harder for like super Earth to degas because the pressure is high and it won't really, it's harder to reach the solidus. For Earth-like planet, the base pressure of the lid will be much smaller, so it's actually easy to melt and lead to easier degassing. Yeah, that's the short answer. And thinking about the initial lid, like so that lid is kind of like also depends on like how much of how much of the surface layer degasses. So that could also be inherited from a magma motion stage. So that's actually one complication that we definitely should think about. I made a very rough assumption, but it could easily be challenged, and that could also matter about like the starting. So like if you look at this figure, like how steep that kind of this starting point could be, it would actually be different.
Thanks.
All right, last chance for a question to our speaker. Well, if not, then I guess we'll thank Yoshi again for this great talk.